Welcome to the Weldfuzion Technical Series presentation on welding process selection, understanding the trade-offs. Let's talk about welding process selection and how understanding the trade-offs between processes can guide you to the right method. This isn't a memorization lecture. Instead, it's about discussing a framework of considerations and applying what we already know about each process. Each situation is unique, but following some basic considerations can help you navigate to the best decision for your application. The American Welding Society recognizes more than 90 different distinct welding, joining, or allied processes. And that's quite a few. So which process is the best? How do you choose the right process for the job? Well, the term best is relative and totally based on context, right? What's good in one area simply won't cut it in another. And it's difficult to choose based on charts, descriptions, and definitions. In the real world, constraints drive decisions. And everyone knows there are always constraints. Aren't we always dealing with time, quality, and cost? 100%. And the goal of any welding operation, whether soldering PC boards, ultrasonically welding plastics, or arc welding beams and girders, is to achieve the necessary quality based on the intended application at the necessary production rate in the most cost-effective manner. Now let's explore some considerations to help you do just that. No matter how advanced or complicated it might seem, process selection begins and boils down to understanding the quality requirements based on the industry you're working in, the code or standard that you might be working to, and addressing the material type and thickness along with the intended application or whatever it is you're making is going to be used for. From there, the process needs to be capable of meeting the deliverables. Something that often separates handheld welding from mechanized or automated installations in some industries. It's also important to consider the environment and location that welding will take place in. For example, will welding be done in a factory, protected from the elements, with plenty of utilities nearby? Or will it be done on a cross-country pipeline, far from power, spare parts, and supplies? All projects deal with common constraints. Time, cost, and quality are going to come up over and over again, and considering these details can help you find the right balance. Now let's start with a little welding history because this can help you distinguish between what process you might want to choose and how technology and innovation have improved things over time to kind of where we are today. So humans have been working with shaping and joining metals for thousands of years. They used what they had available. Heat and pressure from fire and hammers. And that worked for thousands of years. But the Industrial Revolution changed all that. In the late 1800s and early 1900s, there was a need to join new metal alloys with good mechanical properties in a timely fashion. In the early 1900s, welding was largely oxyacetylene for thin sheet metal components and electric arc welding, a predecessor to shielded metal arc welding, what's more commonly known as stick, that was used for thicker, more structural materials. In the 1930s and 1940s, innovation gave way to MIG and TIG welding, or gas metal arc and gas tungsten arc welding. Both were developed initially to improve weld quality and productivity on aluminum. And then FluxCore came along and bridged the gap between stick's outdoor welding capabilities and MIG's manufacturing speeds. Solid state and other advanced processes such as laser welding, friction stir welding, and even resistance welding have all been developed to employ emerging technology to solve old problems and overcome the limitations of earlier welding methods. Each process is an engineered solution to a problem, given the constraints of the time. And that's not to say that new processes are always better or that old processes will automatically disappear, right? I mean, stick welding is one of the most predominant welding processes in the world to this day, and it was developed in the early 1900s. And you see it still being used despite the benefits of MIG welding. Okay, first let's look at oxy-fuel. Nearly every shop has an oxy-fuel setup somewhere. but it's probably not being used in production unless you make jewelry, sweat copper pipe, or work with thick, heavy structural steel, and then it's probably only used for heating and cutting. Nevertheless, oxyfuel is one of the most versatile tools in the shop. And I say tool because it's not just capable of a single process. It's capable of an entire family of processes, ranging from soldering and brazing to welding, cutting, heating and bending, and even more. Oxyfuel is portable and capable of joining many different materials: steel, cast iron, even aluminum. However, it's super slow, has high heat input, which can lead to severe distortion, and has limited thickness capabilities in terms of welding. It also doesn't provide the best shielding, right, which actually comes from the chemical reaction that releases carbon dioxide during the combustion of the gases. So it can't be used for high purity materials or highly alloyed materials like stainless steels. It's just not suitable. In terms of productivity, oxy-fuel welding consists of slow travel speeds and low deposition rates in terms of pounds per hour. So while it was capable of welding on the first automobile assembly lines, it couldn't possibly keep up with today's automotive manufacturing pace. The process is often used for cutting, but limited to steel, and it's very capable of repairs that require soldering or brazing. And I say repairs because production soldering and brazing wouldn't normally employ oxy-fuel anymore either. Not that it's not done, but soldering and brazing are done in ovens with arc or laser processes today. Considering the open flame and the use of flammable compressed gases, that makes the process highly portable and utility independent, right? We don't need power to be able to do oxy-fuel anywhere. But in terms of operation, and considering those aspects, that also brings up a number of safety hazards, right? We're working with an open flame and combustible gases that are parked right next to an accelerant, which is the oxygen. Now, shielded metal arc or stick welding was one of the very first arc welding processes developed, and it's a leap from oxy-fuel in terms of productivity and deposition rate. An electric arc is much hotter than an oxyacetylene flame. The oxyacetylene flame is approximately 55 to 5,700 degrees Fahrenheit, and an electric arc can be as hot as 10 to 11,000 degrees. That creates a very localized heat affected zone and can achieve greater weld penetration. So we have a lot less heat input to the material, a lot less heating of the piece as we form a puddle, and we can get more done. The process uses a flux-coated consumable electrode that is self-shielding from the atmosphere, so no gas is required, only an electric arc welding power source to get the job done. Because the flux forms a slag coating over the weld, it has an excellent draft resistance and is capable of producing high-quality X-ray welds on steel and stainless. However, this process is far from perfect. Sparks, spatter, and slag combine with stub loss for low efficiency. Only about 60% of what you buy actually becomes part of the weld. The rest is tossed away. It's best suited for plate thicknesses that are greater than 1/8 of an inch, and it's not suitable for all metals. It's only recommended for repair welding of aluminum, and the byproducts, sparks, spatter, and slag, make it a poor choice for anything too exotic or expensive. In addition, each electrode diameter has a defined operating range, meaning you can't just crank it up to go faster. There's a limit. Gas tungsten arc welding, or TIG welding, uses a non-consumable tungsten electrode to generate an electric arc. It kind of resembles oxy-fuel welding done with a flame. And this process was developed for high precision welding on aluminum, among other alloys, back in the late 1930s and 1940s. It offers the most precision, accuracy, and control of any arc welding process. It produces no sparks, spatter, or slag, making it very efficient because there's very little byproduct. It can also be done autogenously or without filler metal, so we can just fuse materials together in many cases. TIG can weld more metals and metal alloys than any other arc welding process, and it's capable of high purity aesthetic weld beads that are uniform and consistent. But it's a slow process with a low deposition rate. It's very manual. It has poor cross-draft resistance, right? It uses argon or helium shielding gas in most cases, and any bit of a draft can blow your shielding away and compromise your weld. And it requires more skill than other processes. In the past, TIG has also been quite expensive. So we can't TIG weld everything. And TIG welding is selected primarily on one factor, and that's weld quality. When the application cannot compromise quality, TIG's the choice from an arc welding perspective. Now, gas metal arc welding, or MIG welding, was also developed for welding aluminum at about the same time TIG was. MIG is capable of fast travel speeds, high deposition rates, and long continuous welds. It's kind of the opposite of TIG. Because the wire electrode is spooled up and fed into the welding gun, we don't have to stop and change the electrode. We just keep running. And this eliminates any stub loss, which is the end of a usable electrode that normally goes into trash, right? So the process is gas shielded just like TIG, so there's no flux or slag, which makes it highly efficient. 88 to 99% of what you buy goes into the weld, right? Depending on how much spatter you got in there. Various modes of transfer ranging from short circuit to spray and including various pulsed waveform outputs give it a wide range of application, from thick to thin metals with the ability to nearly eliminate spatter. Not quite, right? Every time the wire touches the part, you can have a chance for spatter. So during this arc start, if nothing else, when that wire's fed down onto the plate, it can generate some spatter. Okay, unlike TIG, which doesn't do that. Now, it does have disadvantages. Poor draft resistance pretty much keeps it confined to the shop unless special provisions are made, right? If you're out on a pipeline trying to do solid wire MIG with shielding gas, you're going to find you got no gas around your weld. So the only way that's done is to build a tent or a block, some type of a screen to keep the wind away and hold the gas where it needs to be. So the welding gun is more bulky than a stick electrode, and it might limit joint access. Despite all the developments in MIG, it's hard to eliminate all the spatter, and it's not high purity like TIG. But that is the goal, right? MIG advancements are striving to achieve TIG-like quality with the benefits of a wire process. And unlike stick, with MIG, you can crank the wire speed and just keep going faster, right? So productivity can really go up if we can control that arc and we know how to dial things in. Flux core arc welding solves the problem of MIG welding outdoors or on dirty metal, which neither MIG or TIG like very much. Imagine turning a stick electrode inside out, so the flux was inside, and then spooling it up on a wire. Well, that's flux core. It has good cross-draft resistance, like stick, but it eliminates the stub loss and the need to stop and change your electrode every, 12 to 15 inches for an efficiency that's kind of between stick at 60% and short circuit MIG at 88%. We're probably talking into that general 70 to 75% efficiency range, because we do have to chip the flux and toss that away. All right, the flux contains deoxidizers and arc stabilizers that are much more tolerant of mill-scale rust and contamination than MIG or TIG. It's possible to do gas-shielded flux core or self-shielded flux core, which can be a benefit out in the field, right? Flux core is also more forgiving than MIG welding and easier to train operators with. Once you dial in your parameters, you can weld along in the flat position, turn around and go vertical up, and never touch your parameters. Try doing that with stick welding or MIG welding one time. It just doesn't work the same. But like I mentioned, flux and slag reduce efficiency, and it must be removed. So that takes time. And then it adds some extra steps. And if you've ever worked in a shop that did flux core, you kind of hear that crunch, crunch, crunch every time you walk around, and as you're walking around all day, because you're hearing that slag. And that's the same with submerged arc welding, which we'll talk about in a bit too. Okay, now a tubular wire is more costly to make, right? Because we have to start out with flat strip, and then we use a tube forming mill and dump the flux in before that final step of rolling that over into a tube. And if too much pressure is used, that can split that seam, and that the wall of the tube is so thin that difficult to feed wires like aluminum that doesn't have much columnar strength are not an option with flux core. Like stick, this is more of a steel and stainless steel solution for structural applications and shipyards where shielding is the key, and they're often welding on material that's less than desirable in terms of cleanliness, mill scale, oxidation, and those kind of things. If traditional welding processes aren't working for an application, you can seek alternatives. Soldering and brazing are non-fusion processes where only the filler metal melts. And that's a good option for thin materials, dissimilar materials, and those with high melting temps that might be difficult to weld, like copper. Small, delicate parts, especially electronic components, are often soldered, right? Because those metallic components are in contact with polymers, ceramics, and heat-sensitive materials. Resistance welding, like soldering and brazing, is a family of processes commonly applied to sheet metal in the auto body and appliance industries. These processes use no filler metal, and they use copper tips in direct contact with overlapping metal, so there's no arc that forms. And the weld forms between the overlapping metal surfaces due to the resistive heating caused by passing high current through the joint, right, between those electrodes that are on either side of the material. And when I say high current, I'm talking like 15 to 20,000 amps. But for a very short time, right? Just a few cycles of a discharge there. So it's not a continuous type of thing in most cases, with the exception of seam welding. Solid state welding includes processes like friction welding, where metals are bonded together using plastic deformation, that ends up being just as strong as the base metals and thus are considered a weld. This opens up new capabilities because we can weld dissimilar metals together that might not be metallurgically compatible, right? Like welding stainless to copper. Try doing that with TIG one time. It's going to be tough. And it allows for welding of crack-sensitive materials like some grades of aluminum that are used in aerospace. There have been many leaps in beam welding, especially in laser welding. These systems provide excellent penetration, fast processing speeds, and high quality without sparks or spatter. Like TIG, it can be very high purity, but they're expensive. There's even a process known as explosion welding, among others, which is typically used for cladding a thin layer of highly alloyed material, right? The pricey stuff, the unobtainium, the expensive material you have to buy for corrosion resistance or whatever property, over a more economical shell, right? Something like low carbon steel that's easy to form, a little bit less expensive, and with that lined, very, very thin liner of material, you can really make some economical parts that way. And explosion welding is something that's pretty interesting. It's again like friction welding. You're using plastic deformation of charges set on the thin sheet to impinge it down on top of the thicker substrate. So quite a neat process. Typically done in mines, and that's something that you may see on the History Channel or Modern Marvels. I think I've seen an episode on it out there. All right. So, and these are just a few processes, and of the many options that exist if traditional welding doesn't work. My advice is we keep it simple if we can. If we're doing things in industry, right, we can look up some references there. We can check how things are commonly done. We can follow our guides. And only employ and only go down the process or down the path of choosing an advanced welding process if other processes don't work, because they're going to be more economical. It's going to be easier to find employees that know how to do those processes. As you get into some of these, especially laser, explosion welding, solid state welding, it changes the game a little bit, right? These systems cost more money. If it's the only option, it's the only option, right? And that's the best choice. But in the other case, we don't want to start out with a laser when we really need a stick electrode, right? So that's kind of where I'm coming from there. Hey, so with a recap of the most common processes that we see used in industry, let's look at some scenarios, starting with number one here, structural steel erection, right? This is the part of construction that happens out on a job site, right? As a building or structure is framed in. Um, if we if we look at quality and inspection criteria for this industry follows the AWS D1.1 structural welding code for steel, which defines the pre-qualified welding processes and procedures that are acceptable to use without any testing, and it specifies base and filler metal combinations, so it really gives you a head start. It also provides provisions for qualifying other processes like TIG in case you need to use it, and procedures for welding, and it also provides provisions for qualifying personnel, right? We see inspection criteria, a lot of design requirements in that code book, so it's very thorough and addresses what's going to happen to these things in service. Okay, the material we're working with is low carbon steel, ranging from about 3/16 for brackets and things like that, to about 1 to 2 inch thick for main beams. Welds are made in a fab shop if they can be, so only short tie-ins and connections need to be made in the field. We're not welding the long beams. This helps to control costs because once you're out on the construction site, cost kind of goes out the window, right? You have to deal with what you have to deal with. There's too many uncontrollable variables. So anything we can do in a shop prior to sending it out to the field, we're going to do it. And that goes the same way with pipe welding and pipe shops. They have spool shops that weld up a lot of the pre-welded joints, and then very few welds need to be made in the field. Okay, the application is load bearing, so strength and mechanical properties are important. We need a strong structure, but it's got to be ductile with good impact and even potentially seismic properties depending on where we are. Welds are done as needed around the other tasks that go into framing a building, right? So one day we're doing concrete, we're using the crane, we're setting things in position, we might be bolting, and then all of a sudden we need to make a weld. So it's got to be quick, it's got to be agile, it's got to be portable. All right. The environment might be outdoors or indoors, so weather, wind, and the elements will likely be a factor. And now think about this. To further complicate welding, when you first get to a job site, the site might not have accessible power. The job could be time sensitive, and welding might just be a tool for the worker. It's not a profession. They're an iron worker. That's just one of their skills, man. So training is a limit. They don't know how to do every process. So what process or processes would you pick in this situation? Well, let me tell you, if you considered stick welding because of its ease of use, extreme portability, and you're able to run it off just about any generator, right, if you need to, you're going to be making short welds, so who cares if you've got to stop and change your electrode? It's not a factor, but it does really well in terms of weld quality in the environment you're working with. And hey, if you're an advanced company and maybe you have some highly trained operators, people with more experience, and maybe you have to make some longer welds because unlike the common welds that are real short, you may have to do something a little different on your job. And then flux core, in fact, self-shielded flux core might be the direction that you're going. Now let's look at another scenario. You're manufacturing lawnmower wheels. There really isn't an AWS quality standard here. right? No AWS-D 1.21 for lawnmower wheels. So the industry uses an application-driven requirement of passing a helium leak test to ensure the welds can hold low pressure without leaking. The material is low carbon steel, so nothing exotic, and it's a lot less than 1/8 of an inch. So we're not dealing with anything thick. Penetration is not going to be an issue. In fact, we're going to have to fight to not burn through. The application is to hold low pressure and otherwise is low stress, right? We're talking lawnmowers. We're not going 50 miles an hour down the road. So very low stress. Production rates need to be super high though to keep up with the lawnmower factory. And welding is done indoors with utilities nearby, and your main constraints are cycle time and cost per part. We're not looking at stick or flux core here, folks. We're in a shop. We can control the environment. We don't want to deal with a lower efficiency wire that's going to take more time to clean up, right, due to that flux and slag. And TIG would be way too slow, right? We know TIG would work, but we don't have the time to wait for TIG to get done. Yes, this here is a classic MIG welding application. And this company was doing everything they could to achieve the necessary quality at super fast speeds. Like I'm talking 100, 110 inches a minute kind of fast. In fact, in this case, the company was upgrading from a short circuit MIG process, and they were implementing new technology called pulse MIG, which would help to pulse into a spray transition and control spatter without putting in excessive heat. So we were seeing a big upgrade here in terms of process capability from standard MIG to a waveform control process. At the same time, in this case, the wheels were all the same size and shape. And let's face it, they're welding millions of them. Handheld welding just wouldn't be capable of hitting the required speeds at the necessary quality, right? There's just too much deviation there, too much going on, too fast. You need too many operators. So they completely automated this process, and then they could have one welder would kick out thousands of rims per shift. So that's a way to look at how manufacturing may be different from fabrication and or repair. Now, let's shift gears and talk about welding aircraft engine parts. Quality here is code driven by AWS D17.1, military specs, and OEM repair guides. The materials welded are normally some form of unobtainium, which is a joke, and that refers to the exotic alloys that are hard to get your hands on because they're so expensive. But they're really highly engineered and high-priced materials, right, for specific applications, obviously in a very stressful, rough environment, right? We're talking an engine that's under pressure and has lots of moving parts. Thicknesses in aircraft engines that when they're welded, except for some of the protective shells and things like that, seldom approach 1/8 of an inch thick, and the application is always mission critical, right? Think of the cost of failure in terms of your lawnmower rim falling off your lawnmower and what could potentially happen versus something happened to an aircraft engine. So we're talking quality here. Quality is of utmost importance. Parts must be dimensionally accurate, right? There's very low tolerance in these things, and things have to go back together and be dimensionally stable so there's no interference and things work the way they're supposed to. There can be no sparks or spatter. That could hinder performance. A little spatter BB in there could probably take out the whole engine real quick. In this industry, again, it's quality over quantity. And except for 911 callouts for repairs, welding's done indoors with aircraft. The main constraint here is quality. Again, did we say quality? Because the cost of parts and lead times are so high and the cost of a failure is so great that the goal is to get it right the first time, right? So here, TIG is the baseline. That's probably the simplest process that we're going to use. And advanced processes like plasma arc, laser welding, electron beam welding are used when TIG just simply isn't good enough. So this is an interesting market to look at, um, how quality is a driving factor. All right. In scenario 4 here, let's consider the problem that drives innovation. Wanting what you can't have, right? When existing processes aren't working, materials or applications are changing, and the constraints escalate. Processes either need to be adapted or we need to develop new ones to accommodate. A simple example could be made of carbon steel pipe. Traditionally, the first pass or the root pass would be made with TIG for high quality foundation. MIG welding, especially short circuit, which deals with a gap much better than other transfer modes, was not allowed on the root pass because of fusion issues, right? So once TIG was put in very slowly, then MIG or flux core might be used to fill and cap the pipe. So there was a huge bottleneck, right? Recently, though, advancements in pulsed MIG technology, mainly what they consider a modified short circuit, have solved this issue. And now TIG root passes in non-high purity applications for petrochemical, oil, and gas have been replaced by advanced MIG welding. Now, the welder can make the root, the fill, and the cap without changing the processes, simplifying the setup, simplifying the equipment, and MIG welding is 4 to 5 times faster than TIG welding. So it drastically improves economics and lowers the number one cost in welding, labor. MIG welding is also much easier to automate, so it opens the door for even more productivity gains. And if you've ever run a TIG route, you know how tough it can be. And switching over to modified short circuit MIG running downhill is so much easier, faster, and simpler. And it's a lot easier to train new operators to do it. So the changes that we're seeing in technology are starting to make welding easier and better in this situation. All right, now we're going to give you some practical advice. You have to avoid the perfect pitfall because we don't have time for perfect, and it's not in the budget, nor is it required on every job. Instead, the goal of welding is to meet the quality requirements based on the intended application, right? And the code or industry standard knows what that application is, okay? So that's why we start there. Keep up with production and provide an economical solution. Remember, the best process is always a subjective interpretation, and it's always based on constraints. Quality is market and application specific, just as welding codes are. And at the end of the day, it's unfortunate, but we can't just TIG weld everything. Haha, joke from a TIG welder. Anyways, to further elaborate on this, if we were to look at the North American market right now, and let's just talk about the most common welder that's sold across the counter, sold to companies, used for arc welding, it's going to be a MIG welder, right? So we've got a spooled up wire, we've got to have shielding gas, it takes more infrastructure to do that. If you were to travel to a different country, right? One that may be developing on a different level, but still at pace with the United States. Because of those constraints of having to have a more complicated infrastructure, having to have spooled up wire, having to have shielding gas supplied with it. Those are luxuries that just not every country has readily available, nor can everyone afford. So we might see something that we do commonly here in the United States is not so common abroad. Does that make sense? And it's based on resources, economic development, and just culture, for example. I don't want to paint it out that we're working always with, first and second, third world nations. Really an issue of that. In fact, when I was in the welding power source industry, I worked with a company called Miller Electric that makes blue machines, and we were putting a lot of time into small little integrated MIG units because it was super easy to do a certain application in the United States. Hey, great, why doesn't everybody do it this way? And we got a call from our cohorts in Europe, and they said, that's not how we do it. And we said, well, we'll get with the times, man. And they said, no, 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 no. If we buy stick electrodes, we buy those from the same company that sells us the welding machine. Once we have to buy shielding gas for MIG welding, we have to deal with a whole different company because the market is different in Europe. So some of those changes are not just economic related, it's structural and distribution channel related as well. So we need to keep that in mind, especially as we look outside of our four walls here at what might be going on around the world. All right, so let's start with the mindset that you need to do process selection. You're going to find people out there that have a favorite process or that like to do things a certain way, and they're gonna lean into that, right? And that's it. They're going to put the blinders on. I'm telling you, don't do that. You need to approach everything with an open mind. Always be prepared to learn, because every time I go into a situation, I always walk away learning something. Hopefully, it's not too painful. But let's walk through this. Okay, start with the basics. Understand the code, the material, the application so that you can dig into it. Consider the key elements like what, where, when, how, and even who is going to do this welding. And then do some research. Look at allowable processes. Look at industry practices. Talk to some solution providers. They may have done something similar before and be able to tell you or make recommendations on what you should do. Talk with your experts, your welders, your inspectors, your suppliers, and other resources that are a wealth of knowledge. And then don't overcomplicate it. If you start with quality requirements, work through the considerations, and talk to the people who actually weld and have experience, right, you'll make good decisions. You have to consider all those factors. There's no one source that's any better than another. If you jump straight forward into a process or a chart, you'll miss the real world constraints. If your solution requires TIG welding with a 3/8 plate outdoors in January, you might have overcomplicated it. All right. Another scenario that I'd like to talk about. I was working with a company in Chattanooga, Tennessee, and they were doing subarc with really thin wire, 1/16 diameter wire. It was really thin for subarc, and they were doing it on really thin material. And I went in and tried to convert them over, higher deposition rate, different wire size, into a metal core MIG welding application, and it stopped dead on the floor. And it wasn't because my solution wouldn't work. My solution was faster. It had less flux, no slag on the ground, right? Because submerged arc welding kind of looks like stick welding, but they dump a powdered flux instead of coating the electrode or making it into a tube. Right, so what they said was the operators were so used to doing submerged arc welding, which happens under a flux, so it generates no arc, and the operators didn't need to wear welding hoods. So that was such a big concern to those folks that they didn't even want to consider MIG welding, right? And another scenario, one of the images that I showed earlier was a structural steel welder welding actually on a crane in Los Angeles, or Long Beach Harbor. And he sent me that picture and said, hey, you're not going to believe it. I came in here. We're welding all these things up with E7018. This job's going to take 10 to 15 years to get through all these cranes. I mean, it's a career. He said, first thing I did, the first day on the job, I brought in my Hobart rep and I said, hey, we need to be flux core arc welding these. And for sure enough, they figured out that they could go, I don't know, 4 or 5 times faster. They could get better deposition rates, you name it. It was all going to go and help everybody put a little more money in their pocket. It was the right solution, the right thing to do. And I said, oh, when are you starting? And he goes, we're not. I said, what do you mean we're not? And he said, well, management was really appreciative. They said it was a great solution, but they said, hey, let's consider a couple of things. We've got hundreds of welders here that are signed up to do this. We've got contracts in place. We already own the business. We don't have to earn it. We're not going up against somebody stick welding trying to put them down. We already earned it. And our operators are all very familiar with E7018 welding, and the cost of requalifying everyone, retraining everyone, and dealing with that was just too much of a nightmare, and they decided to stay with stick welding. And that's perfectly okay. But again, those are some of the things that you wouldn't get from a chart or a description, right? So talking to those people that are out there into it Going to give you some insight. All right. There are many welding processes to choose from to help you solve problems for many different materials, many different applications, even plastics. The best welding process is the one that achieves your goals, provides acceptable quality at the necessary production rate for an economical price. My advice is to start with the basics, work through the considerations, and then balance the trade-offs. Okay, so that brings us to the end of our discussion about how to choose the right arc welding process and when to look for advanced processes. If you have any questions or comments, drop them down below and let's keep the conversation going. Thanks for watching. Thanks for sticking around, and keep your hood down and don't stare at the bright lights.